All right, let's just jump right in. You ever get that feeling that there's some kind of hidden language, organizing the world all around us? A fundamental pattern, hidden just under the surface of everything? Well, today, we're going to pull back the curtain on exactly that.
I mean, really think about that for a second. Every single complex system we rely on, from the world of finance to physics to the algorithms that suggest what movie you should watch next, they all share this common backbone, a silent organizer just working away in the background.
So let's do it. Let's give this powerful, hidden thing a name. So what is it? What is this invisible architecture that's making sense of all the chaos? It's called a matrix. And the key to all this is actually surprisingly simple. We're about to unlock it, and we're going to decode it together right now.
Yeah, that's it, a matrix. And what's wild is just how simple that definition is, right? At its heart, that's all it is, a rectangular grid of information. The two big things to remember are rectangular array and rows and columns. And this is a perfect way to picture it. You just think of it like a perfectly organized grid. We usually give it a name with a capital letter, like A, and then inside you've got all your data points, numbers, whatever, just laid out in this perfect little structure. Okay, so now we know what it is. Let's kind of take it apart. Let's figure out how to actually read the map of this grid. Right, so every matrix has a specific size, or what we call its dimension. And the rule is always rows first, then columns. So if you hear someone say a 3x5 matrix, you know instantly it's got 3 rows going across and 5 columns going down. And every little item inside that grid, we call that an element. And here's the really cool part. Every single element has its own unique address, kind of like coordinates on a map, so we know exactly where to find it.
And this is how that address system works. That little I tells you the row number, the horizontal line, and the J tells you the column number, the vertical line. So if you see something like A sub 23, that just means go to the second row, find the third column. That's your guy. Super simple, but so powerful.
Oh, and just a quick heads up on how these things are written. You're almost always going to see them named with a capital letter, like A or B. And most of the time, they'll be inside square brackets. But, sometimes you might see parentheses or even those double bars.
All right, let's keep building on this. Because once you get the basic grid down, you start to see that there are all these special kinds of matrices. And they all have their own unique tricks. Turns out, not all grids are the same.
So, the first big difference you need to know is between a square matrix and a rectangular one. It's really simple. If the number of rows equals the number of columns, bam, it's a square matrix. A 3x3, a 4x4. If those numbers don't match up, it's rectangular. And this might seem like a small detail, but trust me, it's a huge deal for what you can do with them.
And here's one of those huge deals I was talking about. Only square matrices have this special feature. It's like a hidden spine running right through the middle, and we call it the diagonal.
What's really interesting is that there are actually two diagonals. The main diagonal is the big one. It runs from the top left all the way down to the bottom right. But then you've also got the secondary diagonal, which goes the other way, from top right to bottom left. And these things are absolutely crucial when you get into more advanced stuff.
Okay, another special type to know, the column matrix. This one's easy. It's just a matrix with only one column, and we often call this a vector. This is a really important bridge between the world of matrices and the world of geometry.
All right, so we've gone through the theory, we've looked at the anatomy, now for the fun part. Let's see how this abstract idea of a grid actually gets to work and solves real-world problems. So, take a look at this. This is a classic problem right out of an algebra class, right? You've got two equations, two variables, x and y. And sure, you could solve this the old-fashioned way, but there is a much cooler, much more elegant way to do it.
And that way is to translate this whole problem into the language of matrices. The very first step is to just look at the numbers sitting next to the variables, what we call the coefficients, and then arrange them in a grid, making sure they stay in the right spots.
And there you go. See how that works? The top row gets the numbers from the first equation, 2 and 6. The bottom row gets the numbers from the second one, 4 and -1. And look how everything is perfectly lined up. All the x coefficients are in that first column, and all the y coefficients are in the second. So organized.
Okay, but we're missing something, right? What about the numbers on the other side of the equal sign? To get those in there, we create what's called an augmented matrix, which is just a fancy way of saying we're going to add one more column for those answers. And that's it.
That's the whole thing. The entire system of equations, all the important bits, packed neatly into one single grid. That little vertical line in the middle, that's just there to show us where the original equal sign was.
And really, this is the whole point. We just took what looked like a messy algebra problem and turned it into this single, beautifully organized thing. This is the key, because once it's in this form, you can use all sorts of powerful tools to find the answer. So matrices aren't just tables. They are powerful tools for bringing order to complex information.
And listen, this is just scratching the surface. We just used this grid to organize two little equations. But what if you used it to organize all the pixels that make up an image on your screen, or all the connections between people in a social network? What about the weird probabilities in a quantum system? I mean, if this simple grid can bring order to a couple of equations, just imagine what other chaos it's controlling silently all around us.